So now we've given a brief overview of and given some examples of some classical machine learning models. So let's go into variational quantum algorithms, which are systems that have a quantum part and a classical part. The variational quantum eigensolver is a hybrid quantum classical algorithm for computing the ground state energy of a Hamiltonian. In this system, we have on the left part of the diagram, we have a quantum computation that's parameterized by some parameters theta. And then, of course, we have measurements. And from these measurement results, we get some expected observation from this. And our classical optimizer then takes the results of these measurements and determines whether this sampling was how well it matched our cost optimization criteria. And then we update, the classical optimizer updates the parameters, and these are fed back in a feedback loop. So we have a new set of parameters that are then executed on the quantum processor. And then we have this continuous loop of optimization involving the quantum subsystem and the classical subsystem. Okay, so the next hybrid algorithm or variational quantum algorithm we're going to talk about is QAOA. So this is also a hybrid system with a classical and a quantum part. So here we also have a feedback loop between the quantum computation and the classical optimizer. In this case, the focus is more not as much on quantum chemistry, but more like optimization problems that are, discrete valued, like Boolean satisfiability or other logistical like optimization problems. One example that's used a lot is called the max cut problem, which is a graph problem. But anyway, the structure of the quantum part of this computation is decomposed into a cost Hamiltonian and a mixing Hamiltonian. And this is essentially allowing the quantum processor to evaluate the cost, because the classical problem has been encoded into the cost Hamiltonian, and the mixing Hamiltonian is creating a situation where we are able to explore multiple candidate solutions. So the quantum part is really giving us the ability to sample from a probability distribution that will, with a high probability, give us an answer that meets our optimization criterion. So once we sample from that distribution, our classical optimizer then evaluates it, and we have a feedback loop. I will also mention that this is generally kind of what we're doing overall in quantum computing, as we're sampling from probability distributions that are hard to compute classically. Given that classical AI and variational quantum algorithms are both using a classical optimizer, there is one common issue that can arise, and this problem is called barren plateaus. We know that from calculus, if we're optimizing a function that has a certain compositional structure, like we're optimizing some variable with respect to another variable, but if that variable is a function of some other set of variables, then we have to use the chain rule. And in the context of these cost landscapes, the chain rule will turn into something that looks like this equation here, where we have a product of factors or derivatives here. And what can happen is when each of these products is less than 1, this gradient can go very close to 0. And that's a problem because our optimizer is trying to find areas where the cost is decreasing. So it's looking at this gradient. And when the gradient's 0, the optimizer doesn't really know which direction to go, because every direction looks the same. So this is a problem. It's been researched in classical machine learning as well as quantum machine learning. And there are some mitigations you can do, mostly around your choice of topologies and initial states, activation functions, and so forth. So this is an interesting connection between classical and quantum machine learning.